So, new tools for old sites, the landscapes of stone circles. What I'm going to be talking about today is work that's been undertaken at the University of St Andrews, but in conjunction with a number of other universities around the UK over the last few years. And so we're going to be looking at stones in landscapes and particularly focusing on Neolithic landscapes. So I'm going to start this view and this look at asking things about stones and about the landscapes that they are set in, the purpose of the stones and their origins. And in order to get to the grips with that, we need to see the whole picture. So we need to see not just the stones, but we need to actually see where they are set and to be able to look back in time to look for landscapes that perhaps are not so obvious to us today. So this is landscapes that were there in the past and landscapes that have perhaps now been lost or buried beneath land surfaces. And also we're going to look underwater and look at things that are buried beneath sea floors. I'm going to do this using geophysical techniques mainly, and I'm going to review sites at Stonehenge. We'll talk a bit about the geophysics there, but we'll also talk about some of the geochemistry that's been recently done by others at the site and the implications of that. And then I'm going to go and look at sites in Calanais on the Outer Hebrides, and then we're going to go and finally finish up in Orkney, looking at some of the classic World Heritage sites up there and associated sites that are not within the World Heritage areas. So geophysics and some chemistry, but mainly geophysics, and mapping the stones and mapping where the stones perhaps were but no longer are. Range of techniques, you can see a whole array of them here pictured, everything from things you drag across the ground surface using vehicles like little ATVs and tractors, to things that we carry or push around, and then on the water to things that we are dragging in the water and using from different forms of boats, from everything from very small boats to quite large boats. I'm going to look at geochemistry in a little bit, and there really what we're doing is chemistry, not so much in the field. We do some of that, but also chemistry that results from things in the laboratory. And often there what we're interested in taking material from the field back to the laboratory to analyze. So things that are both consolidated materials, the stones perhaps themselves, but also parts of the landscape, so the soils and the sediments around that. So back to the geophysics, and why do we use geophysics? Well, we use geophysics, it's a remote sensing technology, so we can look often beneath the Earth's surface, beneath the sea surface, and we're looking for changes in physical properties. And so changes in physical properties are things like the electrical resistivity, or how conductive, resistive the ground. We look at density changes, and we use that using gravity methods. We can use the magnetic susceptibility, so how magnetic material is. And we also look at the acoustic velocities, or the elastic velocity of compressional waves and shear waves in the subsurface using seismic methods. If you've watched geophysics on the television and things like Time Team, you'll see people using ground penetrating radar, and that uses dielectric constants in the Earth. And they can also use things like radioactivity and thermal conductivity. I'll mainly show you examples using electrical resistivity and electrical conductivity, as they actually show the greatest range of different values for things in the Earth. And it is that range of values that I'm particularly interested in. In fact, physical materials in the Earth, and we're thinking of stones, have ranges of properties. So you can't have a unique geophysical property or geophysical value for any material in the ground. We have ranges. So sandstone, for instance, has a range of conductivity. And you can compare that perhaps to a clay and see that clays are quite conductive and sands are quite resistive. We can look at that in the same way with the velocity, that a velocity of an unconsolidated sand is quite slow, 1,000 meters per second, whereas the velocity of a consolidated basalt, etc., might be quite fast, so 5,000, 6,000 meters per second. So these contrasts in velocities, in this case, or the contrasts in all geophysical properties, allow us to discriminate things in the ground or to tell differences between different types of material. But as I say, there's no unique signature, so you can't say, if we are looking for a velocity of 5,263, that is uniquely defining a particular material in the ground, a particular rock, for instance. So it's ranges of values, and we're looking at contrasts. So here, using magnetics is a rather nice example of contrast in magnetic signature, showing up as a black and white image of a Roman fort. This is a Roman fort in Germany, and it was acquired using a magnetometer, so magnetic prospecting, and the different parts of the fort, the building foundations, and of course the outer ditch construction and walls that would have been around the fort stand out very, very clearly, because there is a contrast between the natural sorry about that there. There's the natural soils in here and the material all around that. So if we go on and look at some of this now, what we're going to do is look at some of this in a number of different places. And the first place I'm going to go to is down to Stonehenge. And at Stonehenge, what we see is, of course, iconic stones. And that's great. We can see the iconic stones themselves. And what we're really interested in is the different material of those stones. And if you've been to Stonehenge, you'll know that there are different types of stones that we can see at Stonehenge itself. We have what we call the sarsens, and these are actually silicified sandstone, or what we call silcrete. And then we have the blue stones. The blue stones are things like rhyolite, dolerite, tufaceous material, sandstones. And there's been for a long time speculation of where these different materials have come from. And I'll come back to that in some recent papers. This is one by Nash et al. In 2020. But first I want to look in a little bit more detail at some of the landscape around there. So the sarsens, as I say, were these silcrete or silicious sandstones. And if we look at where Stonehenge is in this landscape on Salisbury Plain, we see that it's actually sitting on mainly the grey and white chalk supergroups that are covering most of this area of southern England. We do see limestones outcropping to the south, and off to the north we actually get into some of these sandstone beds, but certainly nowhere close to Stonehenge, relatively speaking, to derive the sarsens from, or derive particularly the igneous rocks from. Okay, the rhyolites and the tuffs, etc. The drift geology in this part of the world is a thin topsoil. We have a colluvium in places in the river valleys, but very, very little really on top of the chalk bedrock. So some geophysics for this landscape, and I'm going to show you first some LiDAR, which is airborne geophysics, looking at the high resolution topography of the area. Then we'll look at some magnetometry, electrical resistivity, electrical magnetic conductivity, and ground penetrating radar. So different ways of looking into the ground and seeing what we can see that's buried, that maybe the human eye cannot see. So starting with the LiDAR, this is a LiDAR data set. It's basically done with a laser flown in an aeroplane or on a drone, and you can see a number of spots in the landscape, or blobs up and down. Here's Stonehenge at the centre of the map in here, and all around it you can see these features, and these are actually burial mounds. So this is just what we can see on the surface, but in very, very great detail. Old field, medieval field structures coming out here to the west. And just note Durrington Walls off to the north there, this big circular bank and henge feature just to the north of Woodhenge, if you've ever been to this landscape. So the LiDAR is helping us pick out, and in fact, this data set picked out in red here, a number of new monuments that we couldn't really see or hadn't seen just by walking the landscape. If I move on to what the magnetics looks like, and that's the magnetometry results for the site here. And again, you can see that a number of features stand out. Okay, features that perhaps we wouldn't have seen in any other way. You can see these white spots and dark spots across the landscape. Now, some of them are modern. Some of these are related to modern things, and particularly because this has been used for effectively war games for many, many years. Salisbury Plain, then we do have a lot of military material that's outcropping in this area. But if we zoom in, this is just an example of some of the patterns of magnetic anomaly that we found. Some very unusual patterns. Each of these squares is about 40 meters by 30 meters. And in some of the patterns we can relate to what we already know about, sort of ditch and burial mound structures that have been ploughed under today, so henges and burial mounds. Some of them we've got no idea, but certainly the form of a lot of these would be hard to explain naturally. And so our job here is to try and understand them further as human-made features. So here's one focused down in with that magnetic gradient in a little bit more detail. And you can see the form of this one. Okay, there's lots of black and white little, what we call bipolar anomalies, dark and white areas. We see these big dark splodges in here, in this circular form. And we see another set of smaller ones within inside that again. So if I'm trying to interpret this from the geophysics, as I say, we see these large outer ones, and we see these smaller inner ones in this concentric sense. If I apply ground penetrating radar, we don't see those individual splotches, but we see outside, we see these kind of big sausage-shaped splodges of anomaly. Now, we don't really need to know, and I'm not going to go into detail what they are. They are geophysical anomalies, and the splodges can be interpreted in a number of ways, and I'll do that in a minute. So there we go, that's the things I'm picking out here. This is electromagnetic conductivity, ground conductivity, how conductive or resistive the ground is. And again, you see a kind of a circular form to this, and in the middle of it, you see some quite low conductivity or high resistivity areas in here. There we go, that's just highlighting them. So here's our interpretation of what's going on. In fact, from the GPR, we think that we've got the remnants of mounds or banks that have been formed, dug out, and the soil placed on the outside of this circular feature. We think these dark splodges in here, which came from the magnetic survey, may well be pits that there were once stones in. And in fact, the inner set of them may well have been pits that could have once held wooden stakes within them. The area in the middle here from the conductivity, possibly something else buried and material replaced, which has got a very much lower conductivity, higher resistivity than the surrounding bedrocks. So you might say, well, that's a bit of an artistic impression based on that geophysics. But of course, we've done this geophysics at many different sites and dug them up already, so we know what is there. We can understand this when we're comparing it to other places. So let's just look at that and sort of compare it to another place. I mentioned this Durrington Walls, and that's to the north of Stonehenge itself. So here's Durrington Walls up here, and here's Woodhenge. Durrington Walls is about 450 meter diameter bank, and it's a circular bank. You can see it's about 4.5, 5 meters tall in the west side over here, and it gets less as we go out towards where the roads have been cut through it. Unfortunately, roads cut through in the 50s and 60s, right through the middle of this feature. But the bank here would be that consistent with what we call a henge. So a henge is you know, we talk about Stonehenge, and everybody thinks of the stones being the henge. No, that's actually a stone circle. The henge of Stonehenge is actually outside of that. And here we see the henge being the bank. So bank is a henge structure. So there's some geophysics. That's a map of the henge, and here's some geophysics. This is the electromagnetic conductivity, and you're seeing now the dark areas here being just outside the bank feature, just like we saw with the GPR on the previous example, and then the lighter areas being on the bank itself. Interestingly, through the middle of this, and this goes down to the east to the River Avon down here, exits down here to the River Avon. We think the entrance to this feature was at this place where the modern road goes through, and there is this kind of Y-shaped feature going through the middle of the site. At the bottom of what in here is a kind of very shallow valley. It's more conductive through here, and most likely that represents where at the back side of this, or the west side of this bank, we probably have winter seepage and water coming up naturally in springs, flowing down through the center of this feature in here. So there it is again, laid on top of Google Earth, just shown in colour this time. Here's the ring of the bank and the ditch on the inside of it in this case, going down to the River Avon at the eastern side of the site in here. That's an artistic impression of what it would have been like, and we actually have had a number of digs in here, and we know that there are features. In fact, there's probably a whole what do we call it? A whole village that's been proposed to be on the inside of this actual feature in here. So let's look at some other data from this place. So that's the electromagnetics again, and this time I'm going to cut the electromagnetics in a kind of a two-dimensional slice through the Earth. And this is the two-dimensional slice showing you in colour here now different conductivities and resistivities for different parts of the section. In fact, at both edges on here, we have high resistivities around the banks and low resistivities in the middle of the ditches. There you can see it again clearly picking out the changes around the bank and the ditch in there. If you look at the magnetics just outside the bank, there's a curious line of these little spots. Each spot is about 2 meters roughly in diameter. And as we focus down in on them more, the geophysics was able to we were able to use it to model what we thought was inside these splodges, and we speculated that there was actually buried stones inside these splodges. Did some further modelling of the geophysics in here to show that. Of course, until you dig it up, you never know exactly what is in there. That was our speculation, that we had a whole series of stones on the outside of the actual henge itself. So a landscape that in reconstruction looks something like that. Actually, unfortunately, as we dug these pits, we found out that our geophysical model was wrong in this case. Rather than stones being in these, we found lots of remnants of charcoal and wood inside the actual pits. So the pits were there, the pits were real, but actually it wasn't stones at all, it was wood. It was causing that contrast in the geophysics that we were seeing. So then a bit more about the stones at Stonehenge itself. And I said earlier we had the upright Saracens and we had the fallen Saracens, and then we have the sandstone, and particularly the altar stone being a sandstone, and then the rest of these blue stones being a mixture of these dolerites and rhyolites. If you look at the geochemistry for the Saracens themselves, we see that there's a number of places in the southeast of England that they could have come from. And of course, up to the Marlborough Downs to the north would be the most likely. It's the nearest concentration of these types of things. And so a recent paper has actually studied the geochemistry of some of these stones and tried to match more precisely the stone chemistry of the Saracens in Stonehenge to them. Here are some of the results of that, and what they're doing is taking all these different sites and mapping a range of chemistries to try and plot against the chemistries of the stones. And the preliminary results show reasonable correlation to this site called Westwoods, which is to the north of Stonehenge, and the most likely place that these could have derived from. Actually, if you look at the statistics, the most likely is only marginally more likely, and it could have still come from many, many different places. The blue stones, well, another set of work has been done on those, looking at the rhyolites, the dolerites, the tuffs and the sandstones. And again, there's good clustering of the chemistries in terms of confidence that they may have come from, or probably came from a single locality. But of course, there's no igneous rocks anywhere within the local vicinity of Stonehenge itself. In fact, as many of you will know, you have to go all the way into South Wales to the Preseli Hills, to the east of Fishguard, to be able to find these types of material. In fact, two of the highest contenders to this are in quarries of the Craig Ross of Elyn for the rhyolites, and Craig Goddard for the dolerites. And so there's been a lot of work there recently. The implications, of course, of this is that, how do you get the stones from here to here? And much has been made about different types of routes for taking them across that landscape. How do they get these stones? Was it all the way along routes like this? Or was it actually taking them down and rafting them along the coast? Well, again, I say these latest papers are starting to say that actually some of the sandstones along the northern routes, land routes, match the altar stone quite well at Stonehenge, and so they're speculating that at least there might be more likelihood for taking them all the way inland. I think the jury is still out in terms of where they took them, how they took them, although I do think that all the way around southern tip of Cornwall would have been out. Yes, very easy to get them up the Avon River, but very difficult to get them around the south tip of Cornwall if you've ever been around there in a boat. As to the Sarsens, well, site 6 up here is the closest and the most likely proposed site for where the Sarsens come from, but I think equally the statistics would tell us they could have come from any of these sites. So any of these routes could be possible into the Stonehenge landscape as it is today. So we're going to go back to Durrington Walls just for a minute and look at some other things that have been going on up there. So here's Durrington Walls again, Woodhenge, Stonehenge, the cursus, and of course the avenue. And again, back to the magnetics, because if you look closely at the magnetics over this landscape, we find here, these are some larger, so we're looking at 2 metre splodges before, and these are about 20 metre splodges in the landscape that are shown up in the magnetics. And in fact, there's a whole series of them that surround Durrington Walls, approximately a kilometre and a half from the main site itself. They're in a concentric form, and if you take GPR through them, you can see that they are a very curious structure. These are a whole series of slices at different, at 5 centimetre slices into the earth beneath the splodges. And you can see in these cross sections here, so this cross sections through one of these features. So that's on the outside, this is coming into it, this is through the centre of it, this is through the other outside, and this is completely outside of it. So you can see that they've got quite a dip in them, and in fact they're about 3 to 4 metres deep, some of these, 20 metres across, so quite significant features. We've cored into these, is it highlighted? Drilled them, cored them, got material back, and in fact we do find material that has been dated to the Neolithic at the base of some of these features, but we also see things all the way up through the Bronze Age in the features. So long-lasting features. We don't really know what they are about. That's how they circle Durrington Walls. They enclose Lark Hill Causeway to the west. They're not exactly on a circle. They're not as precise, if you want, as the location of the stones within Stonehenge itself. But when you start looking at what the landscape looks like around here, the ups and downs of that landscape, what we find is that you can model that in terms of if you want, pacing a distance from the centre of Durrington Walls to each of these features. And if you do that, you see that in this map here, this is kind of like a pacing map. So if somebody were to try and measure off distances from the centre to each of these features at a set distance, of course, we all know that as we walk uphill, our stride tends to lessen. As we go downhill, it gets longer. So if you took the number of strides across a landscape, then you find that actually they are all within the same sort of stride number from the middle of Durrington Walls, even though they're not exactly at the same distance. So quite an interesting set of features. Don't know what they're for. We've got to go back and certainly we would like to dig up some of these more to understand what the geology is. And I think that will help us then understand perhaps what the use of these features might be. Okay, now I'm going to jump to back up north here and I'm going to go out to the Isles of Lewis, particularly the Calanais site that we all know and love. And if you've got a Bank of Scotland credit card, you've probably got the picture of this and the great Lewisian gneiss that it is constructed of on your credit card. There it is. The landscape bedrock is Lewisian gneiss. The stones are Lewisian gneiss. Very little topsoil, apart from deep peats everywhere. And the peat has, of course, buried lots of this landscape. In fact, here you can see a 1.5 metres of peat burying stones of bedrock material, the Lewisian gneiss. And in fact, we actually see walling, and probably Neolithic walling, being buried beneath these deposits of peat. So to understand the landscape there, we must understand the paleo landscape that these were in, and we've got to strip back the peat, and we've also got to look into the water where we might have things that have been submerged, because of course we've had sea level change since the people were first erecting these stone circles in this landscape. So a whole range of geophysics again being used onshore and offshore. I'm going to take us to two sites, one at site 10 here and one site 11 up here. So these are satellite sites to the main Calanais stone circle site, site 1. And if you go to this landscape, you know that there are many satellite sites of stone circles. So first at site 10, this was at the top of the hill, and it was investigated by Colin Richards and others a number of years ago now, because there's a lot of fallen stones there. And in fact, on this thin topsoil, the stones have fallen all over because they could not be dug into deep soils and kept upright. And in fact, at the base of each of these, you see mounds of stone, mounds of small stones, that was an attempt to hold these upright, and of course has failed miserably. There again, big stone, thin topsoil, a few stones around it to kind of hold it and prop it up. Not the kind of craftsmanship that we normally see in building these things. Here's how we think that they were reconstructed at the time. So that's one of the efforts we're trying to make in understanding what's going on in this landscape. That is it here today within that setting. Up at site 11, something different's going on. There we only have a single standing stone. So this is a site on the edge of the hill overlooking the valley. So if you look south from here, you look directly down south to the main Calanais site. And this is the kind of a shelf in the hillside where we have at the red spot there a single standing stone. We've got some shielings, they're marked by these red circles in here. So these are kind of stone huts today. But I'm going to concentrate just on this standing stone here, because it's been reported to be part of the remains of a stone circle at this locality. So here's a community project. We were involved with the Calanais Visitor Centre. And so along these lines, we're doing some electrical resistivity work, and we did some electromagnetics and magnetics and some drone work across here. And here, this is us considering the single stone that is still remaining on the site. So it's quite useful because we can measure the properties of this stone, and we know then what we should be looking for within the subsurface. So this is the electromagnetics. The red spot in here represents the single stone. And really what you're picking out here is the depth to bedrock. So the bedrock is sort of in nice here. It's very, very resistive. So in other words, it's got very, very low conductivity, whereas the high conductivity is associated with deep peats. So at this locality in here on this shelf, we have one stone standing up still, but we think we've got quite deep peat around it. And in fact, we know from the original site 1 that peat has grown up significantly since the stones were built. In fact, back in the 19th century, archaeologists uncovered about a third to a half of the stones there. You can still see the kind of tide mark where the peat had grown up to around the stones. So we know that a lot's going on in that landscape. Here's the electrical resistivity. Not really showing very much at all in terms of electrical resistivity. Some splotches on here, maybe something up here to the north associated with the closest to bedrock, maybe these signatures again closest to bedrock. And you're only really looking down about 40-50 centimeters with this particular instrument in this location. Here's again this electrical conductivity with now this cross-sectional splice, so we can get a feeling in this area where the stone is, the depth of the peat. And we think it is probably at least 1.5 meters in places through here, so certainly beyond electrical resistivity work. And here's the magnetics. So this is the location of the individual stone, and we can see, as I say, the signature of it, that it's got this black spot, white spot, and that's quite common for a magnetic anomaly to have a sort of a high and a low, if you want, a positive, negative associated with it. There are a number of these other black, white, black, white, black, white, black, white, and so we would speculate that these are actually buried stones because they've got the same signature as this black, white spot of the extant stone. But you'll also notice in here this big kind of L shape, well, or maybe even cross shape, with a positive, negative, black, white feature. Now this is very curious, and this is actually characteristic of something that has been hit with lightning. Right? And we don't see this very often in the UK. See it in dry, arid areas, but you certainly don't see it in the UK. And that's because it's very wet here. And when you've got soils or features in the ground that are very wet and they get hit by lightning, the lightning conducts away from it and doesn't leave a signature in the ground. So we tend to see these in dry areas or where the lightning hits bedrock without any material on top of it, any wet material. So it hits a very resistive bedrock. And of course, the Lewisian gneiss is a very resistive bedrock. So if we put that into context, here's all of our singular anomalies, and here's the anomaly for the lightning strike. We would speculate that the lightning strike is actually at the center of where these singular anomalies occur. In other words, at the center of what would have been once the stone circle. Coincidence? Or perchance that it happened there? I doubt it. I mean, what came first? Did they put a stone circle up and the lightning hit in the middle? Or did they have something in the middle here that was attractive to lightning? Maybe a big stone was here. Maybe a huge tree was in the middle. Huge trees for this part of the world, of course, are not very common. But maybe back when this was built, there was one. Today, we've got this deep peat sequence. And so we need to get beneath that deep peat to the bedrock to see what the remnants of this lightning strike might have done to the bedrock. So this would involve an excavation at this site. There's another view of it. So a curious place. So what I'm going to end with is looking not at land data now, but looking at marine data for trying to find stones using geophysics in these landscapes. So this is just showing us a reconstruction from about 8,000 years ago to present of what sea levels were doing, and this area offshore called Doggerland, where the 8,000 or more years ago you could have walked from southern England across to the continent. You'll actually note up here in Orkney that we also had a lot more land mass back then, and as sea levels rose, it flooded that land mass. So certainly when the first people came to Orkney, they were coming into a landscape, not a seascape in much of the time. So we want to look here and see what was going on at that time period. So here's a reconstruction. If you know the Orkney Isles, then Kirkwall's down here on the main Orkney Island, and over into here is the Bay of Firth. And I'm going to spend some time looking in here at features on the sea floor and comparing them to things we get in the World Heritage sites, places like the Ring of Brodgar, Ness of Brodgar. So we'll look at the Bay of Firth. As I say, the stones in this landscape is all Devonian sandstone. That's what almost every standing stone and every burial mound is made of. Fantastic material for building with, breaks up into these really great building size slabs. So it's Devonian sandstone, that's the Omanophyte, of course, that is famously made out of it. And the drift deposits there are till and some deep peats again, so burying some of the features within the landscape. This is the bathymetry, seafloor depth, in the Bay of Firth, and you'll see some deeper parts or basins and some shallower parts. Here's our sea level curve when sea levels were rising from 9,000 to present day, from about -10 meters to 0 today. And you'll see that it's gradually risen. All these points are places where we've measured that kind of rise through that time period. If we look at it 8,000 years ago, then there is where the sea was, and we can see that it didn't cover the whole of the bay. There was an inner basin in here, probably a freshwater loch, and probably a couple of other freshwater lochs in here. That red dot represents the site we're going to look at on the edge of this freshwater basin at about 8,000 years ago. By 5,000 years ago, we started to flood this area and flood this feature on the seafloor. And it's certainly, by 3,000, the whole bay is flooded in a similar way to it being flooded today. This is looking into the bay, and those are the old freshwater basins. And the site I'm going to focus on again is on the side of one of these freshwater basins, just down in there. This is what it looks like on the sea floor. So it's a circular feature that we've found on there. It's about 1.5 meters in elevation above the sea floor. And if I peel back the sea floor and look subsurface, and this is seismics looking at that, you can see that around the circular feature, the Devonian bedrock has been bent or has been laid up in a concentric fashion. Now, Folding is something that can do that, geological folding. But in this part of the world, the bedrock, the Devonian sandstones are very flat-lying. We don't see many tight, and this is about a 40-meter diameter, tight dome. You don't see anywhere, in fact, I've never seen anywhere in this part of the world, these tight dome-like features. So there it is in cross-section. We see the bedding dipped on both sides of it, quite steeply, but we see it flat-bedded in the centre. 40 meters diameter, and what we're going to do now is I'm going to take you and swim you from the centre to the outside, and we're going to photograph it as we go, and I'm going to measure the dips. So let's make it to those photographs. Here at the centre, you can see it's very flat-lying rocks. Flat-lying, starting to dip more, and then it becomes vertical. It's vertical and concentric at the outer 5 meters. So it's almost like a big platform where it's like a polar mint with steeply dipping rocks for the last 5 meters on the outside of it. There you go again. Steeply dipping rocks that are bedded closely together. Now here up at the Ness of Brodgar, we can see flat-lying rocks being used everywhere to build wall-in structure. But we also do see the use of steeply dipping rocks, very tightly packed together. You'd almost say, when you look at them here on land, that's natural material, that's outcrop. Now we know it's not, because it's set within these other building layers in here. But the style of it is exactly that which we see on the seafloor. 40 meters diameter, well, as we go and look at here, the maze hat, which is a ditch around it that's 40 meters in diameter. Of course, the ditch at the the ring of Brodgar is very, very much larger than that. But again, we see this modification of the natural stonework around that locality. So on the seafloor here, we have a 40-meter diameter ring of upstanding stones. Has it got a natural origin? Well, it might have an igneous core, I suppose, and could fold the rocks up just in this one place. There is a little igneous activity on the isles. There's some very, very thin dikes that come through. I mean, it could have a sedimentary origin, like something of a water escape structure, but again, we don't see very many of them like that, and it's got such uniform form, it's hard to imagine that would be the case. Is it built by humans? Well, it was flooded about 8,500 years ago, and that's before before there was a big population in the Neolithic building monuments, building any sort of structures on the islands. It's on the banks of a freshwater loch. It's a kind of a nice location. It was flooded by the sea, possibly dramatically. It might have been sudden. It could have been gradual. We're not exactly sure the time period it was flooded by over it. We do know people were there, so even if this was a natural feature, what did those people make of this? What did they think about this circular feature being flooded at that point in time? Might never know the answers to this. We keep researching and we keep trying to find out what did go on. So we've come to a number of different sites, a number of different ways of looking at them, looking at the stones and looking at the landscapes of the stones and the stone settings. In order to understand, of course, landscapes and people and their use of these landscapes in the past, we need to understand things in a very broad context. We need to understand what they're doing, and the evidence for what they're doing is often left in the stones. Geophysics and certainly geochemistry can help in that understanding. We need to do all this together, ultimately, to have a greater understanding of the past and the people and their lives. So thank you for listening, and if any questions arise from this, then I'm sure through the webcast you can get my email address. I'm always happy to answer questions. Thank you.